Okay, so let's pick up from where we left off last lecture. So we were discussing going through some of the sample problems in homework 5, the problems that you don't need to submit, right? So we skipped a few problems on conditional probability because I didn't want to have to read, large problems when we were running out of time. So let's finish up uh, some of the discussion today, and then we'll move on to the next topic. Okay. So so let's look at this problem, right? Problem number 12 over here. Um, so another, medical testing type problem. And the reason why I want to go through this is so that you see uh, what are some of the formulas that we use in problems like this, right? So there are a couple of probability related formulas that you should remember, and they will come in handy for everything related to this conditional probability, right? So let's start by writing down something that's quite um, obvious, um, such as probability of not B is 1.0 minus probability of B, right? So this is always true, right? So something not occurring, well, you just say 1 minus the probability of that event occurring. So this, another um, identity that is useful in the context of conditional probabilities is this one, right? So probability of an event A equals probability of A given E multiplied by probability of E plus probability of A given not E multiplied by the probability of not E. Okay, so this is a standard um, formula on um, conditional probability, which you can derive, right? So every formula involving conditional probability can be derived very easily from the definition of conditional probability, right? So we have the definition which says A given B equals probability of A intersection B divided by probability of B, right? So this is the definition of conditional probability, and this is the, if you remember this, then you can derive pretty much anything and everything that you need from this, right? And you can derive this from this information and this definition, right? It takes all of, 30 seconds to do the algebraic simplification using this and that rule in order to arrive at this one. Okay. Still, that 30 seconds or 1 minute, you don't have to spend it if you already know this formula, and then you can just, go from there. Okay. So now this problem is designed, first and foremost to make you familiar, or to get you to look at these formulas and make it, get familiar with how to use these formulas in simple problems, right? And then there are a couple of other problems. I think there is, yeah, so problem 11 is somewhat similar. And then there is also problem 3. Yeah, so problem 3 is also quite similar. And I'm not going to go through problem 11 because it's quite similar to problem 3, which I want you to, carefully go through, right? Because it's actually a pretty simple problem. And unless you walk through the steps carefully, you will not internalize some things that we learn in the class. Um, so can, if you, a few more of you turn on your camera so I can have a slightly better idea of what, uh, how students are doing. You can do it. I'm sure it's not that hard to turn on the camera. Okay, very good. So that's a good number. Okay, so so yeah, because I think, looking at solutions or having somebody work out a problem that's very similar to this one, I think is not that helpful. I think you need to sort of, if it requires some amount of looking through the notes and finding the right definitions, I think all of those steps are important for you to, get familiar with the material and, you know, get more fluent with doing problems. So I'm not going to go through problem 11, but of course, after you submit, you can see all the solutions, just like we have done for problem set 3 and 4. Or I guess I gave you solutions to all the problem sets, right? So, okay, so let's take something like this. So you're asked probability of A intersection B, right? And you know that you're given the conditional probability of A given B and the probability of B. So this is a straight application of this formula, right? Which relates the probability of A intersection B, the probability of B, and the conditional probability of A given B, right? So you plug this into that formula, right? You plug these numbers into this formula, and you should be able to get this answer, right? So, so this is probability of A intersection B bar, or A intersection not B, and that's again pretty much the same sort of thing, because you again have probability of B, from which you can find probability of not B, and from then on, this problem part B is very similar to part A. Okay, and probability of A you can obtain using this formula, right? Gives you probability of A given E and probability of A given E bar. And in this case, you have probability of um, so you have probability of A given B bar and probability of A given B, right? So you have those two pieces of information, and then you need these two probabilities, which are here, right? So once again, if you plug those in, you will get the answer, and probability of B given A can once again be determined using the standard definition of conditional probability. Okay, so all of this are problem 12. All the 4 parts are pretty straightforward, um, you know, applications of these conditional probability definitions. And there is, of course, there is a last part, which is quite similar to the problem that we discussed in class. So it's not going to be you're not going to find any surprises here, right? So once again, you have a rare condition, right? The probability of the disease is 1 by 20. And the false positive rate you can see is 10%, whereas the disease rate is just 5%. So you can imagine that there are going to be lots of, if a random person is tested, you can imagine that it's more likely that the person doesn't have the disease than it is likely that they will have a disease, right? So it's the same kind of thing that you get with many other medical diagnosis type of problems. So are there any questions? Okay, so So the probability questions are generally not going to be that hard, right? So the hardest thing about probability is, to make sure that you don't make mistakes, right? You need to be able to compute without making mistakes. With counting, sometimes you need to sort of understand or get the idea of how to count. But counting also has a significant component of, not, making a mistake in terms of, thinking about, if you think about permutations instead of, combinations, well, that's one kind of error, right? And sometimes you don't figure out what is the problem that does this map to, and then again you can sort of end up with a very complex calculation. And a third kind of error that you make is that it involves, you know a union type of problem. You're taking the union of sets, and you need to apply, inclusion exclusion principle, and then you simply added, instead of applying the inclusion exclusion principle. So there are a few mistakes that you can make, and you need to, through by working out problems, I guess, hopefully you will get better and you'll get more confidence in your ability to do these problems without mistakes. And that's pretty much what we are expecting in the case of probability as well. So work out enough number of problems, have some confidence in your ability to approach these problems methodically, and be able to solve them. Okay, so the very last problem here is, induction proofs. And I made my life simpler by just picking 3 problems from the reference I gave you for looking at induction proofs, right? So let's go to that. Right, so I gave you this reference, right? So if you go there, all 3 problems, all 3 subproblems of problem 15 are worked out here, right? So you can just go and look at the solution. Or of course, what you should do is you should try to prove those, some of those yourself, and then you can if to verify your solution, then you can go through this and find the problem here. Again, there are like 15 problems here, so finding 3 problems among those 15 should not be too difficult. Okay. Any other questions on this homework? Your next chance to ask questions is Tuesday, right? So when at your recitation, when your TAs will be back, and then you can ask questions. Anything else about the midterm is coming up in 2 weeks. So should be prepared, right? In 2 weeks from now, you'll be prepared. Okay, good. Let's move on to the next topic, which is so the next topic is recursion, right? So we are going to talk about recursion, which is one of the most versatile and fundamental techniques in programming as well as algorithm design, right? And we are going to try to make some progress in understanding what recursion is and how to use it, right? So as we go through this unit, we will learn a little bit of functional programming, because you're learning functions and sets and whatnot. So now you can do, uh, get to know how all of this math and functions that you learned is actually applicable to doing uh, very simple types of programming tasks. Okay, so it's not going to be anything heavy duty, right? So, but you would uh, at least get a taste for using mathematical notation for actually solving problems of an algorithmic nature. So I say induction and recursion because the two are very closely related, right? So uh, in induction, we talked about base case and the induction step, right? Base is an induction step. In recursion, we talk about base case and recursive case. And in the case, so the way the two relate is that recursion kind of starts at some number n, and then you call the function. So there is a function on n that ends up calling function of n minus 1, n minus 2, and so on, all the way up to, say, function on 1, right? So this is a typical nature of how recursive calls work. So you start at the top and you go down, and induction is simply traverses this chain in the opposite direction, starting at the basis and then you know uh, establishing how something is correct for not only the base case but all the other cases that are reachable, right? So the two will go hand in hand in computer science. So we will this is why we talk about induction and then recursion, and then you'll see again and again how they come together, right? So we are going to talk about recursion in to application of recursion to three problems, right? So one is what we call as recurrences, right? So these are specific types of equations, recursive equations that typically capture um, you know properties of algorithms, right? So you want to say, hey, what is the runtime of this algorithm? And typically you would write down a recurrence to capture the runtime of the algorithm, and that's why this says T, which is stands for time, right? So what the way to read this is that if you have an input to this algorithm of size 0, right, or basically the empty input, then the algorithm takes 1 unit of time. If you give it an input that is you know that is of length n, then it's going to uh, you know uh, spend time proportional to n, and then it's going to require additional time which is proportional to 2 times uh, the time taken to run the algorithm through 2 halves of the input, right? So this is the kind of thing. So this particular recurrence comes up in a class of algorithms called divide and conquer, right? So what you do is in order to solve a problem, what you do is you take the input, you do some processing on it, and then you divide it into pieces, and then you recursively invoke the algorithm on each of the pieces. Okay, so that all may sound abstract, and that's fine at this point. Later on, when we actually talk about recursive functions, you'll get some examples of exactly why you get these sorts of equations. For now, what we are interested in is, given these types of equations that relate uh, that specify the runtime of algorithms, how do we solve them, right? So these recurrences, we want to write them down and we want to be able to solve them, right? So that's one type of use of recursion we'll talk about. And once again, it has a base case and recursive case. Then we will talk about recursive functions and how they are used in programming. So, here is an example for summing up a sequence of numbers, right? So this is our sigma I equal to 1 to n of I, right? So this is a summation that we have done like a dozen times and proved a dozen times so far. So if you want to compute this, then you can write a recursive function definition like this, which says that if the input is 0, then the sum of numbers 0 through 0 is simply 0. So let me just call this 0, just right. And it says that sum up to n can be obtained by first computing sum up to n minus 1 and then adding n to it, right? So this is a very simple recursive function for computing the sum up to a number n, right? So it's basically computing 0 plus 1 plus 2 plus up to n, right? So to compute this, you can take this function and give it to, there are languages in which this is more or less a program, and then the system will evaluate it and print the answer for you. So in the third application, which kind of goes hand in hand with these writing functions, is often you want to compute on complex data, right? It's not just numbers. Sometimes it is sets, sometimes it's arrays, sometimes it's matrices, sometimes it is what was I trying to say? So the point is that it's not just integers that you are working with, right? So you're working with something data that has more structure than integers, and you can use mathematical concepts that we have studied so far to construct more complex data types, such as strings, and use them in your program, right? So once again, for these data types, you have base cases and recursive cases. Base cases are basically finite sets, okay? Because if you're doing programming, then obviously you can't work with infinite sets. Everything has to be finite. So you're going to work with finite sets. And so we will typically take finite subsets of the set of integers and the set of real numbers, right? And then the recursive case, where you are constructing more complex data types, that's going to be done using the set construction operations that we have seen before, such as Cartesian product and set union, right? So all of this is going to become types in this language, and you can define the type of your data and then write more complex and more interesting programs using these data types. Okay, so that's just a high-level outline of what we are going to do in this unit, and pretty much the rest of this course will be spent mostly on this unit, right? So we are almost at the end. So the first thing we're going to do is we're going to talk about recurrences, which, as I said, are used in analyzing algorithms, right? And most often you are interested in analyzing the runtime of algorithms, but sometimes you may be interested in how much memory it uses and so on, right? So for this course, of course, we are not going to talk about memory or anything like that. We're just going to talk a little bit about time, because time is something that we all understand, and we don't have to know a whole lot of computer science in order to understand, what time means. So we're going to start by talking about this problem called Tower of Hanoi. Okay, so it's a simple game. The goal of the game is to move all the disks from this post 1 to, I think, the second post, right? So you want to move everything from here to here, but you can't just pick it up and move it there. You have two rules, right? The first rule says that only the topmost disk can be moved, right? So the disks have to be moved one at a time, right? The story is that these are all made of gold, so you can't possibly lift more than one disk at a time, okay? The second rule is you cannot place a smaller disk on top of a larger disk. I'm sorry, you cannot place a larger disk on a smaller disk, right? So you always have to put a smaller disk on a larger disk. Okay, so these are the two rules. So the question is, how do you solve the puzzle and how many moves will be needed? Okay, the story goes that this is this tower exists in a temple in Asia where there are monks who are trying to move. There's a stack of 64 disks, and they are trying to move it from one post to the next, and they have been at it for many years, and they are required to keep doing it. But unfortunately, when they do finish the task, the earth will be destroyed, or maybe the universe will be destroyed. Okay, so they cannot stop, and they have to keep doing this until they reach the end. And of course, people are interested in knowing how many more years can we live before the universe is wiped out. Okay, so we are interested in knowing, okay, suppose there is so there are two things we need to do here. One is, what's an algorithm for solving this puzzle? And second is, how long will this algorithm take to run? Any questions? So how many of you have seen this puzzle before? Okay, so you have seen this. A few of you have seen it. And more of you may have heard of it without knowing exactly what it is. Good. So here is a way to solve it. If you have, let's say, 3 disks, right? So you take the topmost disk and move it to the spare post, okay? And then the second disk can be moved to the second post, okay? And now you can move this disk back on top of this, right? So that's what we're done here. So now, so you have done all of this because only now is the largest disk free, right? So now you can move this largest disk to another peg, right? So you want to move it to the last peg. So in order to make that move, you need to take everything above it, right? So essentially you need to take everything above the last peg and move it onto the second peg, okay? And because you cannot pick up 2 pegs in one shot, you have to go through a series of steps like this. First, move this over there, and then move the second one over to the second post, and then move the largest disk into the last peg here. And now you can, of course, put the smallest one on top, but that doesn't help because you need to put this next. So you need to first move this over here. That's what we have done here. And then now you can move this back there. So that is the configuration here. And then finally we move this back and we are done with this, right? So how many steps, how many moves has it taken? 7, right? So 7 moves. So there are 1, 2, 3, 4, 5, 6, 7, right? So 3 disks has taken 7 moves. How long do you think 64 disks will take? Greg.
2 to the 64th power minus 1.
Right. So that's the answer to the problem. So let's figure out how to get there. Okay. First is to come up with a general algorithm, right? Because all we did see here was how to do for 3 disks, right? So what if you have n disks? So what is the algorithm? Okay. So here is where recursion comes in handy, because you can say, what was my main strategy? The main strategy was to take everything except the bottommost disk and move it to the next post. Okay. So first, what I need to do is I need to take all of these n-1 disks and find a way to move it to this one, right? And then I can move the last disk over here, right? And then now again, once again, I have these n-1 disks here, and I need to move them back on top, right? So, so that's what this picture illustrates. So you take the n-1, move them to the second post, then move the largest disk back to the third post, and then move these n-1 again back on top. Okay. So if you write that down as an algorithm, then here is an algorithm move stack, which takes 3 parameters. The first parameter is the number of uh, disks that need to be moved. And then you have 2 other parameters that specify where do you start from and where do you end up with, right? So you are starting from um, peg 1, and then you want to end everything to end up on peg 3. So this step 1, right, can be described as an instance of the same algorithm, except that it is applied for moving the top n-1 disks, right? So, but we do want to move it to peg 2, right? We don't want to move it to peg 3, we want to move it to peg 2. Okay. And then we just want to move a single disk, right? So I call it move disk because I'm just moving a single disk. So step 2 moves a single disk. And then third step, I want to move the stack back on top of 3. So I guess it should say 2, 3, right? So move stack of n-1 disks from peg 2 to peg 3. Okay. So this is the algorithm for Tower of Hanoi. And you can see it's a pretty simple algorithm because we looked at it recursively. We are able to come up with such a small definition or description of how you go about doing it. Okay, so this is technically we also have to define a base case because the base case occurs when you have a stack of only one disk, right? So in that case, these 2 moves are not applicable because you're trying to move a stack of size 0, right? So the base case is obtained by simply removing the recursive invocations of the same algorithm, right? So we call this as recursive invocations or recursive calls. Okay, so because we are defining the move stack algorithm, and if the move stack algorithm ends up using itself, then that is what we refer to as recursion, right? So these are recursive invocations, right? So alternate term for invocation is a call. Okay, so in the case of when you are working with real programming languages, the term that you're going to be using is function and call, right? So this will be a function, and this will be a call to the function. Okay, so In this course, we might, as easily use the term, algorithm, invocation, and so on. Okay, so but they're all mean basically the same thing. So any questions? I hope this algorithm is quite simple to follow, but if not, you should, stop me here and get your questions answered. Any questions?
Yeah.
Yeah. Go
How do you, so when you do step one,
on.
so how do you move all of the pieces except the last one to the second one?
So this is an invocation of the same algorithm, right?
Okay.
So you just go back here.
Oh,
So you just say, okay, I have to move n minus 1. Okay, so let me forget for a moment that I'm trying to move n disks, right? Let me just think that I have to first just move n minus 1, right?
okay.
And apply the same technique, right?
Oh,
And
okay.
then
Yeah.
you'll say, okay, now I have to do n minus 2. Okay, let me do n minus 2 and then come back. And then let me do n minus 3 and so on. All the way until you get to 1, right? And then in the case of 1, it's pretty clear what you need to do. You just move that disk and then you come back. So now you will be in a move stack of, you'll be trying to move a stack of 2. So let's try to do this here. This is exactly what is going on in this example, right? So right here, you start with, let me just write it as M. I don't want to write M move stack because it's just going to take me a long time to write. So I'm just going to call it M of 3, right? So I'm going to apply the move stack algorithm working on 3 things, right? And what it says is, never mind, I need to first do M of 2, correct? Because that's what this algorithm says. If I want to do M of move of n, then I need to first do move of n minus 1, right? So I need to do M of 2, and following the same logic, I need to do M of 1, right? M of 2, in order to do M of 2, I need to do M of 1, right? So let us write this down in a way that maybe makes it a little bit easier to see what's going on. So I want to do move of 3, right? So let me write down what I need to do. I need to do move of 2, right? And then move disk the third disk needs to be moved, and then I'm going to do move of 2, right? So notice that I've just copied this algorithm over there, right? So that we can see what is our algorithm, so that it's easier to follow exactly how I'm carrying out the steps one by one, right? So the move stack has 3 steps. One is to move stack, then to move disk, and then to move stack, okay? Instead of writing move stack, I'm just writing M here because I don't want to, it takes too long to write that, right? So move stack of 3 involves 3 steps: move stack of 2, move disk of 3, and move stack of 2, okay? So now what I'm going to do is I'm going to say, okay, so I'm just going to create myself some space and just move those instructions here: move disk of 3, move stack of 2, okay? And now let me expand what move stack of 2 is, right? Move stack of 2 has, again, 3 steps: move stack of 1, right? And then move disk of 2, and then move stack of 1, okay? Now, we know that to move stack of 1, that is a base case, right? So in the base case, we only have a single operation of moving a disk. So what we are going to do here is we are going to replace that by moving a disk, then moving the disk 2, and then once again moving disk 1. Okay, and the same way, what we can do is we can rewrite M2. M2 again involves M1, MD2, and M1, and M1 again involves MD1. So I'm kind of crossing these out. I'm sorry, that was a mistake. I should not have crossed out MD3. Okay, so whenever I expand, like move disk of 2, move stack of 2 has been expanded into these steps. And each time I do that expansion, I kind of cross it out to kind of say, okay, I have expanded that into the steps. Okay, so now what I have done is I have basically taken my recursive algorithm and expanded it out. And then you will see that this is, I'm sorry. I'm sorry. So I expanded that. So now you'll see that the first step is move disk of 1, right? Which is what I have done here, right? So this is actually the first step shown here is exactly this, right? And the second step shown here, right? You can see is also this, right? Moving the disk 2. And the third step is moving the disk 1 back on top, right? And then moving disk 3, right? Which is the fourth step here, right? And then this is the fifth step, sixth step, and seventh step, right? So if we go through our algorithm and follow it step by step, we will get exactly the steps that are shown in this sequence. So does that help?
Yeah.
Okay, good. So I just want to make sure that that's a good question, because I think, yeah, it is necessary. Sometimes, well, obviously I know recursion well, so I don't realize that, trying to go through the steps like this is necessary to sort of get a better idea of how this works. So now that we understand what this algorithmic description means, we can then ask the question, how long does it take? Okay. And this actually has a very simple answer, right? Because we know that in order to move a stack of n, right, we have to move a stack of n minus 1 twice, right? So the act of moving a stack of size n requires us to move a stack of size n minus 1. So, so we can say that the time to move n disks is going to be the time to move n minus 1 disks here, plus the time to move n minus 1 disks here, plus the one move here, right? So you can say time, or you can say how many moves are needed, right? So you can say that, so this is, you can think of it either as time or number of moves, right? So then you arrive at a recurrence like this. The time for the algorithm to run on input of size n is equal to 2 times the time for running it on an input of size n minus 1 plus 1. Okay. And once again, for the base case, we just have one operation. So we can say that T of 1 is simply 1, right? Because all that you need to do is to move a disk of size 1. Okay. So this is how we start from an algorithm and arrive at something that relates or something that corresponds to the runtime of the algorithm. Any questions? Okay. So now what we are going to talk next is, okay, given these types of recurrence equations, is there a way to find a closed form solution to these equations, right? So these are like, you know that there is some relationship between, the runtime when the input is n and the runtime when the input is n minus 1, but it doesn't tell you exactly what that runtime is, right? So we want to find a solution to these equations that'll tell us exactly how long it runs. And there are several techniques for solving recurrences, and we will explore them one by one. Okay. The very first technique is called plug and chug, which is just means that you're going to try to take this recursive definition and expand it out, and then try to right? So you just expand it out at a few steps. So for instance, in this case, you have T of n equals 2 T of n minus 1 plus 1. Okay. So now you expand it out by saying T of n minus 1 equals 2t times, right? So the same equation, right, you apply to n minus 1. Then that'll tell you that it is equal to 2 times T of n minus 2 plus 1, right? So we have 2 times, and then the substitute for T of n minus 1, right? So this is what we call as expanding out the recurrence, right? So we substitute for T of n minus 1 in terms of T of n minus 2. So that is 2 T of n minus 2 plus 1 plus 1. Okay. So this is, so what we have done is we have taken T of n minus 1 and replaced that by this expression. Okay. And now we simplify. So that'll give you 4 times T of n minus 2 plus 2 plus 1. Right? So typically this step is called plug, because you are essentially substituting T of n minus 1. You are so basically you can say that you are plugging in to go from this step, the first step, to the second step. You are plugging in the definition of T. Okay. And then to go from second step to third step, you are doing essentially some kind of algebraic simplification, and that's called chug. Okay. So you alternate the two steps until you start seeing a pattern, right? So basically you will see a sequence, right? So, and we have all solved problems where you are given a sequence and you're asked, what is the pattern in that sequence? And so what we are trying to do is to do that expansion and identify the pattern in that sequence. Okay. So if you keep expanding, then you'll find at the next step, what you'll get is 8 T of n minus 3 plus 4 plus 2 plus 1, right? And then if you do one more step, 16 T of n minus 4 plus 8 plus, right? So what will be the last step? right? So you can see that to observe, to find the pattern, you see that when you go from n to n minus 1, the coefficient is 2. When you go from n to n minus 2, the coefficient is 4. When you go from n to n minus 3, the coefficient is 8. When you go from n to n minus 4, the coefficient is 16. So we could guess that what we are getting is 2 to the power k t of n minus k, right? Sort of fits, right? And you can see you can arrive at this pattern by just seeing that each time I'm decreasing n by 1 and multiplying the coefficient by 2, right? So anytime you do that, you end up with something like 2 to the power k. And then you can also see that this number, right, is actually half of this one. And then the next one is half of that, and half of that, and so on, right? So this is going to be 2 to the power k minus 1 plus 2 to the power k minus 2 all the way to 1, right? And where is this going to stop? It's going to stop when n minus k equals 1, right? Because that's when you'll reach the base case, right? When you reach the base case, there is no expansion further. So this is going to stop when you reach 2 to the power n minus 1 times t of 1 plus 2 to the power n minus 2 up to 1, right? And we know that t of 1 just involves moving a disk, right? So t of 1 is nothing but 1. So we can just cross that out because that's just 1, right? So the runtime or the number of moves is given by this sequence, which adds up to what? It's a geometric sequence we have seen many times, right? 1 plus r square plus up to r to the power k or whatever, right? So the solution to that we know is r to the power k plus 1 minus 1 divided by r minus 1, right? So let us substitute that over here. So r here is 2. So we'll say 2. And k is n minus 1, right? So if k is n minus 1, k plus 1 is going to be 2 to the power n, and then minus 1, and then 2 minus 1, right? The denominator, again, you're substituting 2 for r. And so this is going to just become 1, right? So 2 minus 1 is just 1. So the answer is 2 to the power n minus 1. Okay. So normally what you do is once you identify a pattern, you come up with some kind of equation like this. But that's not enough because at this point, it is mostly a guess, right? You're not, you may not have gone through all the steps to verify exactly what the solution is. And in general, it is not possible to, be really sure that your guess is right, okay? So what you do is then you check, you plug it back into the algorithm or into the recurrence and verify that it actually works for a few small values, okay? So if it doesn't, of course, you know that your formula is wrong. So, but if it works, it still does not mean that your algorithm is correct. So typically what you would do is you would use induction to verify that your formula is correct. Okay, so let's try to do that. So we are saying that the solution is 2 to the power n minus 1, right? Or let's write it in a different way. Okay. T of n equals 2 to the power n minus 1. Okay. So let's go through an induction proof. we have the base case, right? So here n equal to 0, and t of 0 equals, if you substitute this formula, then that is 2 to the power 0 minus 1. Well, let's not do 0, I'm sorry. Let's do n equal to 1, right? So because that is our base case, not n equal to 0. So let's put n equal to 1, then we get t of n equals 2 to the power 1 minus 1 equal to 1, right? Which matches because in the base case, we are just moving one disk. So there is exactly one move. So t of n correctly gives us the value for the base case, right? So now we do the induction step. So we know that move stack of n, or rather, I'm sorry, that's not what we are interested in, because we have already taken care of that. Okay, so in the induction step, we know that t of n so we need to prove t of n plus 1 equals 2 to the power n plus 1 minus 1, right? Because that's, if you plug n plus 1 here, then right-hand side will become 2 to the power n plus 1 minus 1, right? So let us start by taking the definition of t to the power n plus 1. That's equals 2 times t of n minus 1. Okay, so this is equals 2 times by induction hypothesis, right? So we can substitute, we can say by induction hypothesis, t of n is 2 to the power n minus 1. And then now you simplify, 2 times 2 to the power n is 2 to the power n plus 1. Oh, I'm sorry, this is, right? So the recurrence that we have, I just, made a mistake in writing the recurrence. Okay, so this is the recurrence, 2 times t of n minus 1 plus 1, right? So, so that's what it is. So this should also be 1. So now if you multiply 2 times 2 power n should give you 2 to the power n plus 1. 2 times minus 1 will give you minus 2 plus 1. And then that simplifies 2 to the power n plus 1 minus 1. So, right, so this is what we needed to prove, and we are done. So the point about plug and chug is that, yes, you can use this expansion to look for the pattern and then guess a solution, but then you do have to prove it, okay? So these types of induction proofs are going to be quite straightforward. And so I don't think it's going to be a big difficulty for you. Most of the time, the difficulty of using plug and chug is in this pattern recognition, right? So you can do this manipulation, but what you will find is that it is in general, in some cases, you can very easily spot the pattern, and there could be other cases where you may not be able to spot the pattern. And so this makes the plug and chug somewhat unpredictable, right? So it is a very general technique, right? It is going to work no matter what the recurrence is. But, seeing the pattern may not be very easy in some cases. And so in that sense, it's like a hit or miss, right? So if you find If you spot the pattern, then you can go ahead and do the rest of the steps. But sometimes you cannot spot the pattern, and that makes this sort of a difficult technique to apply. Nevertheless, we see an example of how to do it for uh, you know towers of Hanoi. So, but because we don't want to spend the time to do this expansion and plugging it in. Again, as I tell you, the plug and chug technique is a very general technique. It's not does not limit you to specific types of recurrences or anything like that. On the other hand, it is a very labor intensive and uncertain process. Okay, so what I'm going to do is I'm going to teach you two techniques which are limited to certain types of recurrences, right? So they are not necessarily applicable to solve anything and everything in the world, but they are much more methodical. So there is a certain procedure, and if you follow the procedure, you have the solution, right? So there's really nothing more to it. Okay, so we are going to start by talking about homogeneous linear recurrences. So what does homogeneous mean? Okay, so these are linear recurrences of this form. Okay, so so I want you to be comfortable with this summation notation, but what you might find useful is that whenever you see a summation and you're not sure exactly what it means, you can just expand it out, right? So if we expand this out, this is a1 f of n minus 1 plus a2 f of n minus 2 plus, I don't know why it makes that into a3 times f of n minus 3 plus dot 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 a d times n minus d. Okay, so these a1, a2, a3, they are all constants. Okay, so why this form? Well, it's the main point is that these are linear. What that means is that inside the f, there is something of the form n minus a constant. Okay, and that so this is I'm sorry, I misspoke. So let me state what is the linear and what is the homogeneous. So the linear part is that f of n is dependent upon some f of n, right? It's not like f of n equals f of n minus 1 times f of n minus 2, right? If I said something like that, then that won't be linear. Okay, so because all I have is a multiplication by a constant, so that's why this is called a linear equation. Okay, it's called homogeneous because you have this multiplication by constant, and all the terms here are multiplied by a corresponding constant, right? So the structure is very uniform, right? And that's the homogeneous part of it, right? It's not like you have f of actually I'm not able to give you an example, so I won't. Okay, so but anyway, the main point is that as long as you can write the equation in this form, right, this form, you are going to be able to use this method. Okay, and let's do that for the Fibonacci series that we wrote down before, right? So this is the Fibonacci series we saw in the last class. So f of n equals f of n minus 1 and f of plus f of n minus 2. So that's a homogeneous linear recurrence as per this definition, right? So instead of having so many terms, we just have two terms, right? But otherwise, it is an equation. that satisfies this format. Okay, so so the reason why we work with equations of this format is is that they have exponential solutions of the form f of n equals x to the power n for some x. Okay, we know this already because people have studied equations of this form, right? They have studied recurrences of this form, and they have found out that a recurrence of this form has a solution f of n equals x to the power n for some x. Okay, we don't know what the x is, right? So that is the part that we have to figure out. Given a particular recurrence, we need to find out what is the value of x. But we know already that a solution of this form will work. And so how do we find x? We're just going to substitute into the equation, right? So we know that f of n equals f of n minus 1 plus f of n minus 2, right? And we have already said f of n is x to the power n. So we're going to say fn, we're going to replace f of n by x to the power n equals x to the power n minus 1 plus x to the power n minus 2, right? We're just substituting. We know the solution is already this form. So we're just substituting f of n minus 1 with x to the power n minus 1 and f of n minus 2 with x to the power n minus 2, right? And now we can divide everything by x to the power n minus 2. So we'll get, so that is x squared equals x plus 1, right? So we are just dividing right? So R right? So that gives us a quadratic equation. Have you seen this quadratic equation before? This specific one. Can you tell me where you saw it? Greg?
We saw it in the closed form solution for the Fibonacci numbers.
Right. So when we were trying to prove this property of this solution for Fibonacci, we made a point that note that this particular funny looking number is actually a solution to this quadratic equation. Okay. So anyway, go ahead. Let's go ahead and we will solve this quadratic equation in a little bit. Okay. But more generally, right? So you have an equation of this form, and whatever we have done so far will work for. Okay. So I showed you an example for the specific case of Fibonacci, but this way of replacing f of I by this kind of substitution, the known solution, right? So there's a typo here that somehow there is a y that came here. I don't know why, but just ignore this. It is just supposed to be f of n. So so we can apply that, and so again you'll be able to divide all the terms by x to the power n minus d, and you will end up with a polynomial equation, not a quadratic equation in general, a polynomial equation, and a polynomial equation of degree d minus I. Oh, I'm sorry, degree d, right? So because the maximum degree of this is I equal to 0 to d. So the maximum degree here will be just d. So a polynomial of degree d, how many roots does it have? So what's the degree of a quadratic equation? 2, right? So the degree is the maximum exponent, right? So in a quadratic equation, the maximum exponent comes with x square. So the exponent is 2. So quadratic equations have a degree of 2. Okay. And you know that they have 2 roots. So in general, a polynomial equation of degree d has d roots, right? So it's basically has the same number of roots as the highest degree. Okay. So so here is what we do. We find the roots of this polynomial. Okay. And then the solution, general solution, is of this form, right? So because we already said it is of the form x to the power n, and we solved for x, right? That's what we did here. All this equation solving here is meant to find what this x is, and then the value of the x is nothing but the roots of this equation. So we know that the solution is like r1 to the power n. Okay, so we can say f of n could be of the form r1 to the power n. But this is not a general solution because there are d roots, right? So the most general solution for this equation is going to be of the form f of n equals k1 times r1 power n plus k2 times okay. So you don't have to worry about why this is the case. It's a property of linear recurrences that you can take solutions like this and combine them linearly like this, and the solution just works. Okay, you don't have to worry about why. You just take it as a granted that this is the process you use for solving linear recurrences, right? You set up this equation and you solve, find the roots, right? And obviously I'm not going to give you anything more than a quadratic equation to solve, right? There are ways to solve higher degree equations involving higher degree polynomials, but that's not something that we are going to ever encounter. Okay, so and finally, what you need to do is you need to find what are these constants k1 through kd. Okay, and this can be solved because you are not only given this recurrence, but you're also told what is f of 0, f of 1, f of 2, and so on. So you have any number of base cases that you can use, and they can be used to find the values of k1 through kd. Okay, so let us use that to solve this problem, right? So we already said we reduce this to the quadratic equation x squared minus x minus 1 equal to 0, right? So from this linear recurrence, we arrive at this formula as we saw here, right? So we start with f of n and we plug in x to the power n as a solution, and then we get this equation on x, right? So let's start with that equation and find the solutions to this. So that is minus b, which is plus 1 plus or minus b squared, which is 1, minus 4ac will be plus 4, right? Divided by 2a will be 2. So this is 1 plus or minus square root 5 divided by 2, right? So rather we have root 1, which is 1 plus square root 5 by 2, and then root 2, which is 1 minus square root 5. Did I make a mistake? Don't remember. I may have got this sign wrong somewhere, okay? But If there is, just correct it later, right? So essentially, let's see what it is. Okay, I think this is correct, right? So if you see any mistake in the solution to the quadratic equation, let me know, but it looks right to me. So we have R1 and R2. So then we can say the solution to, so f of n is k1 times right? And now what we can do is we can set n equal to 0. Then we'll get an equation that says f of 0 equals k1, and this whole thing when n equal to 0 will become 1. So that drops off, and then when we set n equal to 0, once again this whole 0 will become 1. So we'll get f0 equals k1 plus k2, and we know that f0 is 0, right? And then, right, we know that Fibonacci number of 0 is just 0, right? So f1 is k1 times 1 plus square root 5 by 2, because we are setting n equal to 1. So that's, or let me just write it that way, plus k2 times 1 minus square root 5 by 2 whole power 1. Okay. And if you simplify, you will find that this is equal to k1 plus k2 divided by 2 plus k1 minus k2 square root 5 times. So all I have done is I've just separated these two terms, 1 and square root 5. So you get k1, k2, right? So divided by 2, and then k1 times square root 5, right? Minus k2 times square root 5. Okay. And once again, we can set this equal to 1 because that's what we know the two, because we know that the Fibonacci 1 is 1. And then if we go ahead and solve, do I have? Okay, so let's do that. So we have these two equations, k1 plus k2 equal to 0, which simply means k2 equals minus k1, right? So that's what we get from this equation. Then let's substitute the value of k2 into the second equation. So then we will get k1 plus k2 divided by 2 plus square root 5 k1 minus k2 divided by 2 equals, let's substitute k2 equal to minus k1. So we have k1 minus k2, I'm sorry. Right? So k2 has to be substituted by minus k1, right? So that's what we have done here. K2 has been substituted with minus k1. Similarly, on the second term, we are going to do square root 1 times k1 minus k1 by 2, right? So once again, for k2, we have substituted minus. So k1 minus k1 is going to become 0. And so we have, and this whole thing is equal to 1. That's what we said, because f of 1 is 1, right? So so this is equal to 1. And let's do some simplification. So square root 5 into 2k1 by 2 equals 1, right? So this is k1 minus k1 is 2k1, right? So these 2 and that 2 will cancel out, which implies that k1 equals 1 by square root 5. Okay, so we have the solution for the equation, which is so we can replace k1 by 1 by square root 5, which is what we did by solving it, and k2 by minus 1 by square root 5. Okay, and you can check that this is the equation that this is the solution that we used in our induction proof before, right? So by using this linear homogeneous approach, you are able to come up with this nice, interesting solution, right? Because obviously, looking at the this Fibonacci series and how it is always an integer and how it has a simple form like this, we definitely don't expect that its solution has square root 5 in it, right? But we just apply this standard technique, and then we go through a few steps, which are all mechanical, right? It's possible that some of you didn't quite follow the steps, but I'll assure you that it is a mechanical process. And if you didn't follow it, it's just a question of, you may have to sit down and go through the steps yourself, because sometimes we don't understand, algebraic simplification unless we do it ourselves, right? But otherwise, it's a very mechanical process. At the end of it, you have a solution for the recurrence relation. Okay, so that's how it works. So let us stop here, and we will pick up from here on the next time when we will describe a second method for solving recurrences. Yeah, if there are any questions, now is the time to ask. Otherwise, enjoy your weekend.
Sorry,
Yeah.
could you go up to the slide where like it had a step after the general solution?
Yeah, I hope I can. Right. So here is, you have this polynomial, you find the roots of the polynomial, right?
Yeah.
And then you are told that the general solution involves all of the roots, right? So instead of just saying x to the power n, you are going to apply the exponent n to each one of the roots, okay? And then you're going to say, oh, by the way, there could be some constant coefficient in front of that, okay?
Yeah. So for like the general solution, we would be required to like find all of the constants, right?
Yeah, correct. But
Okay.
again, if you think about it, right, quadratic equation and solving k1, k2 takes long enough, right? So you are not going to ever see more than a quadratic equation.
Yeah.
If that is the question you're asking.
Yeah.
Yeah, because what is the purpose of asking you to do anything more complex, right?
Okay.
Unless
Thank you.
I just want to torture you.
Slightly unrelated question, but I wasn't sure who to ask. If
Yeah.
I'm not sure if a future class that I'm planning to take is a prereq or a co-req with a certain class, do you know who I should contact?
So the program director, right? So okay, for the honor students, right?
Mm-hmm.
Michael Bender
Okay.
should be the person that can answer the question. Okay.
Mhm.
You can
Okay.
ask me and I will answer it if I know the answer. If
Okay.
not, then go to Michael Bender.
I guess then you might know the answer. CSC 260 is
Yeah.
listed as a prereq for CSC 220 on one website, but a correc on another part of the website.
So we are going through a process for making it a correc,
Mhm.
and I can find out when that is going to be effective and then get back to you.
Great. All right. Thank you.
Okay. So if you don't mind, send me an email.
Mhm. All right.
That
Thank
way,
you.
I don't, forget and do something else.
Yeah.
Right.